This is a video about antennas and interference at low frequencies, where the antenna is a small fraction of a wavelength. First, I'm going to demonstrate an electrical field sensor that I'm going to build starting from this toroid. It has 8 turns on both sides. It can work as a perfect balun if you have a magnetic loop outside and you want to isolate it from electrical things inside. You can use this in your cable. The transmission is, as you can see here, the markers are set on 1, 2, 3, 4 megahertz, and the sweep ends at 5 megahertz, where the loss is 12 decibels in this 50 ohm system. I'm going to design this for medium wave, and that is marker 1 megahertz, and the loss is what did we see? It's minus 4.7 dB, and we can see here it looks like an inductor of 8 microhenry. To optimize transmission at 1 megahertz, I need to put about 1 nanofarad in parallel. So this is what we have now, and I stop and put in the capacitors. Now, with 1.5 nanofarad at each end, it looks like this. The resonance is at about 1.5 megahertz, and the apparent inductance at 1 megahertz is 10 microhenries, and marker 2. And at 2 megahertz, the apparent capacitance is 500 pF, and on the resonance, the impedance looks like 250. So the coupling between the primary and the secondary is not perfect, and we have losses in the iron. But still, for the range 0.5 to 1.5 megahertz, this is a reasonable transmission. Now I have put a secondary winding with about 130 turns on it, and the primary is still 8 turns with 1500 pF across it. Now I'm coupling to it capacitively, and since the transformation ratio is about 250, that is 130 divided by 8 squared, I should make the capacitor 250 times less, and that's 6 pF. So here is 6.8 pF, and let's see at the transmission. It looks like this, with a maximum at 2 megahertz. This means I need a little bit more capacitance than this. Now the capacitance is 22 pF, and I'm still coupling very loosely. And the frequency response is like this. And the feature at the beginning here is an artifact of the instrument, and to demonstrate that I will just make the coupling a little bit more strong here. So now the coupling is stronger, but the capacitance when winding wires around like this is very small. The signal level has increased, and the feature here is weaker. We have a reasonable performance between 1 and 2 megahertz, The impedance is very far from 50 ohms. The standing wave ratio is near infinite over the entire frequency range. And that is typical for a wideband design with a very small antenna. One could load it with resistors, but that would make the signal a little bit smaller, or perhaps quite a bit smaller. The proper sensors to use with this transformer here would have a capacitance to infinity of about 40 pF, because they are series connected, and together they would then form 20 pF to match the result I just presented. Now 40 pF, that is a sphere with a radius of about 40 centimeters. So it's a huge thing. I don't want that. I should have had many more turns on the toroid, but it takes a lot of time to use such a thin wire and make very many turns. So this is going to be good enough, because I'm, after all, only going to listen to interference with this antenna. So I have to put here at the center a capacitor. I have just put the capacitive coupling into the network analyzer to see where the resonance is, and you can see here it's about 3.2 megahertz. So I put something there to get the resonance where I want it. Now I put 12 pF at the center, the little ceramic capacitor. I'm still coupling capacitively, as you can see here. The frequency response is approximately what I want. You can see there is a maximum a little bit above 1 megahertz, and the signal goes down to below 500 kilohertz or so. The impedance is horrible. It is nearly zero at some frequency, and it is nearly infinite at another frequency. If I put 50 ohms in parallel with this antenna, like this, the impedance is good at 1 and 2 megahertz, but it becomes very bad a little bit higher. I move one marker, you can see number 1 here. Sorry, it is 0 at 1.3 megahertz, and it's good at 0.7, and it's not good. So putting just putting 50 ohms is no good. To make the radio see a reasonable impedance, one would have to put an attenuator in series here. If I connect it to a standard spectrum analyzer here, you can see it picks up all sorts of things. This is probably what it's intended to be used for, and that is interference from the computers I have around. Now I can switch the polarization. It is now horizontal, and now it is vertical. And there is something not very different. Here the electric sensor is arranged for vertical electric fields, that is vertical polarization. I have connected it to an Aphedri net SDR and to a laptop. And here we have Linrod running with some AM station at what is it? 1.27 megahertz. And here is the S meter. You can see the signal varies a little with time. And it plays some music. It's one of the strongest stations in the band. Well, it was a little time ago. I can switch to another station. This one looks strong. So it's stronger. So I stay for this station for a while. Now I try to change the polarization. So now it's horizontal, and I twist it. So here is a minimum, is this kind of angle, and I turn it here and get a minimum with this angle, while vertical is strong. It's quite clear that this electric field is vertical, although we are inside the building and it's not so clear how wires and other stuff around here affects the fields. But this is a good electric sensor. I can use it to look around the computer. And it's not surrounded by strong electric fields. We have some somewhere here, but not much. There is a power supply also. I bring it. And even the power supply is not a big source of electric fields. That's interesting. Now it's time to make a magnetic sensor. Here I have 3 ferrite rods, and they are wound with a winding with about 1 centimeter between the turns. And then there is a secondary winding which is just a single turn at the middle of the rod. It looks like this on the network analyzer, and you can see the impedance is very high. Only at 1 megahertz up here it's a little bit there. I mean, there will not be much current through this coil when it's fed from a 50 ohm source, so I need a lower inductance. Now there is about 3 centimeters between the turns. That is 3 times fewer turns then, approximately. And the response is like this. You can see the old trace and the new trace, and the coupling to the pickup coil is a little stronger at 1 megahertz. It's maybe 3 dB more at the higher frequencies. And we can see on the impedance that it is clearly inductive, and at 1 megahertz it's about 50 ohms and reactive. And we can see that the fewer terms cause reduced sensitivity. If I click marker at this point, that is 560 kilohertz. That's where these fewer turns makes a worse antenna. So this is about the correct number of turns to use for a wideband ferrite antenna. Now I can tune it to bring the signal level up a little bit by putting a capacitor in series. So here is 4.7 nanofarads in series, and I can press on it to make the short circuit. Let's look at the transmission. And so I press on it and release, and you can see it's maybe a dB improvement. So I leave the capacitor in place. Now I placed one layer of foam tape on the bunch of ferrite rods and pulled the wire from one end outside the foam tape. We now added one more layer of foam tape, and on top of that some PCB material to make the connection more robust to the cable, like this. The coupling, as you can see here, has not changed at all. I will save these traces. That's display and data to memory, and for that display and data to memory. And now I will put a screen on top of everything. So this is what the magnetic sensor looks like with a screen on it. It's just some thin copper foil, 1 1/4 of a turn, and isolated to not be a short-circuited turn. What happens here is that the signal is a little bit weaker, and if we look at the Schmidt diagram, this is what we have now, and this is what it was before. So the inductance is a little bit smaller. I should have used a couple of more turns on the ferrite, but the difference is not big. What happens when the screen comes on the rod is that all the magnetic field lines come out through this little hole. Before we had lines coming like that at the center. So now it doesn't matter where along the axis I have this until I come to the end, where all the field lines come out. Now I will listen to this thing. The magenta track is the magnetic antenna. And I'm listening to the electrical antenna, which is connected through a 10 dB attenuator. The ferrite rod is not a good antenna, but you can see here we have similar field strengths, and both of them are now optimized for the best signal level. The electric field now is horizontal for this station, and this is the direction of the magnetic field. Now I can show the difference between these antennas. I take this one and I move it to the computer. And I'm not listening to it, but you can see on the red track how much interference it picks up. And now I can switch and listen to this signal. I do it in the polarization graph. It comes as the vertical. But the magnetic field is quite local, as you can hear. So this is now the magnetic antenna. I switch back to the electric one. I have to make it fairly pure. Easiest by X and back. And I have to find the same station. Here. And then I take the electric antenna. I did this before, and you see. When I do this, I make the antenna better because I couple electrically to something big. And the same here. And the other end, it doesn't matter which one. So the computer is a source of magnetic interference only. That is very interesting. It tells us something how we can reduce problems by not picking up these magnetic fields and convert them to currents into wires that are surrounding our equipment. Here red is magnetic and blue is the electric field. At another place in the house, we are listening to the electric field now, and I switch to the magnetic field here. And the magnetic is a little bit better, as you can see also on the S meter. So I go back to the electric field here. There is some QSB, as you can hear. And the antenna is sitting here. I'm bringing it near something. And we lose a bit because there are electric fields around this fluorescent light. An interesting thing is that it's less on some other lights. So this one is okay. And now I go for the magnetic. Of course, now it became strong because I coupled to this cable. That's unfair. So I switch for magnetic field. It should be 90 degrees. And I'm up here. We don't pick up the electric field at all. I don't know why the magnetic field is stronger here. Very odd. It must be all the plumbing and cables and whatever in the house that makes the field strength vary from place to place. I should go outside. That will be tomorrow or some other day. And the computer is of course again a lot of magnetic, but not much electric. So these are two very interesting tools when one goes for interference fighting and building better antenna systems. The magnetic sensor needs a handle. It's sensitive to electric coupling. If I put my hand here, the level goes up significantly. That's because I induce a voltage in the single turn that the screen constitutes. So I will put a handle on it so that there will be no capacitances to the screen that are significant enough to couple current into the single turn.